circuit symbols are something that is easily overlooked but so important if they are going to come up. So here we have a cell, and more than one cell added together makes a battery. Now, the thing that you call a battery in everyday life isn't actually a battery, it's a cell. If you have two cells, or two things that we normally call batteries, together, that makes a battery. And it doesn't have to be two, it can be 3 or 4, it can be 1. Here we have an open switch and a closed switch, a lamp, an ammeter, which needs to be in series, a voltmeter, which needs to be in parallel, a resistor, a variable resistor, a fuse with our line going through it, a thermistor, diode, which will only go in one direction, light emitting diode, and light dependent resistor. Here we have a series circuit, and a series circuit is one that you can run your finger all the way around without any interruption and end up at exactly the same place, only going over things once, not having to backtrack or go over things twice. Now, in our series circuit here we have lots of ammeters, and in a series circuit the current is going to be the same at every single ammeter. So if this is 1 amp, then this one's going to be 1 amp, this one's going to be 1 amp, and then this one's going to be 1 amp. Now, a voltmeter has to be in parallel, and if this is measuring 1 volt across this bulb, 1 volt across this bulb, 1 volt across this bulb, and 1 volt across this bulb, what we need to do is to add them up, and the total supply is going to be 4 volts. So the potential difference and the resistance are actually summed in a series circuit. A parallel circuit has branches, so we can go here and then here, but we can't go all the way around without overlapping ourselves or backtracking on ourselves. So this is a parallel circuit. Now, in a parallel circuit, the rules for current and voltage are different to that than in a series circuit. In a series circuit, the current is the one that is summed. So if this one had 2 amps and this one had 1 amp, the one up here next to the cell would be 3 amps. The potential difference across components, however, is the same. So if this one was 2 volts, this one would be 2 volts, and then this one here would be 2 volts. There is a lot of maths in physics. There's no way we can get away from this. Physics could be described as maths with a lot of words in and a few graphs. So we need to be really, really good at our maths, and these are the rules that I get my students to follow when we are talking maths questions. First of all, get your magic physics pen. Now, my students laugh at me, but this is what I call it. So get a coloured pen, get a highlighter, get a different colour pen to the one you're writing in. Circle all of the numbers that you can see in the question. Use the units to work out what these numbers mean. Get your formula sheet, find an equation with all of these bits on, write down the formula. Now, this is generally, unless they give it to you, going to be your first mark. Write the numbers under the formula in the right place, do the maths, because that's generally only worth 1 mark, and then add the units. So even if you've forgotten your calculator, you can still get loads and loads of marks by doing all of these things. Now, units are so important. You have to learn these, but there's just no way we can get around this. For any of the maths bits that you need help with, pop over to my website and look at the books that I've got there. Loads and loads of stuff to help you with the maths and physics. You're also going to need to be confident in your standard form, your significant figures, and you're going to be confident in your rounding, because these are the sort of things that are really, really likely to come up in the exam as extra little bits, but might not be something you spent too much time on in your physics lessons. My website has loads of resources to help you with this. Here we have the potential difference. We have current, and we have resistance. Resistance is measured in ohms, those are those that funny shape there. Current is in amps, and potential difference is in volts. Here we have a capital P, which is for power. We have current and potential difference. Our potential difference is measured in volts, our current is measured in amps, and power is measured in watts. Distance time graphs can be used to look at a journey, and there are different features in distance time graph that you need to be aware of. So when we have a horizontal line, this means the object is stationary. When we have a line that is going up, this means it is moving at a constant speed. And then when we have a line that is returning back to 0, it means they're going in the opposite direction. If we want to find the speed from a distance time graph, what we need to do is to find the gradient of the line. And that will give us distance over time. Now, velocity time graphs can look very, very similar to distance time graphs, but they're showing different things. So our horizontal line going across, that is now showing a steady speed. The line that is going up is now showing acceleration. And if we want to work out the distance travelled, that is going to be the area under the graph. So here is the equation for looking at speed, distance and time. Speed is measured in meters per second, distance is measured in meters, and time is measured in seconds. If they give you any of these in non-standard units, remember you have to convert them into standard units. If we want to find acceleration, we need to take the final velocity minus the initial velocity and divide it by the time taken. Time taken is going to be in seconds, initial velocity is in meters per second, final velocity is in meters per second, and acceleration is in meters per second squared. Another equation that confuses people, this P here is momentum. Then we have M is mass and V is velocity. The mass is measured in kilograms, velocity is measured in meters per second, and momentum is in kilogram meters per second. Now, if you cannot remember that momentum is measured in kilogram meters per second, just remember that momentum is meters times, or mass times velocity, and the units of mass are kilograms and the units of velocity are meters per second. So momentum, kilogram, meters per second. Now, momentum is a tricky one. This is an area they could throw in a really, really nasty question. The important thing for you to remember is that with momentum, we cannot lose anything and we do not gain anything. So we have to have the same momentum before as we had afterwards. So if we have two objects, say ice skaters or cars, travelling towards each other, and one of them has a mass of 5 kilograms and the other one has a mass of 7 kilograms. One of them is travelling at 2 meters per second and the other one is travelling at 4 meters per second. If they join together to make one object, at the end, which direction would they be travelling and how fast they would be travelling. So for this, first thing you need to do is decide which end of the paper is positive and which end is negative. Now everything that is travelling towards the positive, so going in this direction, now becomes a positive, and everything that is travelling towards the negative in this direction now becomes a negative. So what we need to do is to work out the momentum for, let's call this A and let's call this B, momentum before, and then we can use that to work out the momentum afterwards. So momentum for A, momentum equals mass times velocity. So our mass is 5, our velocity is -2, so that will give us -10. Momentum for B, momentum, mass times velocity. Oh, did you notice I forgot my units? Oh dear. So our mass is 7, our velocity is +4, so that gives us plus 28 kilogram meters per second. So the overall momentum is going to be A plus B. So that is -10 plus 28. So that is going to give us plus 18 kilogram meters per second for the overall momentum. So now we know the overall momentum, we can use that to work out the direction and the velocity at the end. So the two objects have joined together, so 7 plus 5 equals 12. So this object now weighs 12 kilograms. Its momentum is plus 18 kilogram meters per second. So we have P equals mv. So we have 18 equals 7 times v. So 18 divided by 7 is going to equal 2.6 meters per second. And because this is plus 18, this is going to be plus, which means it's going to be moving in this direction towards the left-hand side of the paper. So complicated question there, but if we think about these things carefully, if we think about them logically, it looks like a complicated question, but it's actually just the same equation 3 times. Next we have F equals ma, so F is our force, m is our mass, and a is acceleration. Acceleration is measured in meters per second squared, mass is measured in kilograms, and force is measured in newtons. There can be lots of forces on a moving object, and you need to be able to look at these forces and work out which direction these are actually going in. So in this first box here, we have 5 newtons in one direction and 10 newtons in the other direction. Now, when we're talking about directions, you can always give a direction a positive and a negative. So we can say anything moving to the left is positive and anything moving to the right is negative. So we now have positive 5 and negative 10. This just turns into a maths question. So what we can do is work out the overall force is going to be -5 newtons. Now this gives us a direction as well, because minus things are going in that direction, and it's going in that direction with a force of 5 newtons. Again here we can have +15 and -12. Overall this is going to be +3 newtons, so it is moving that way with a force of 3 newtons. Again here, +10 -2, that is going to give us +8 newtons overall, so it is moving in this direction. When we have +2 and -2, the overall force on this is going to be 0, so it's either not going to be moving or it is going to be moving at a steady speed. And to break up the maths a bit, here are some really cute kittens. Here we have weight equals mass times gravity. And weight is measured in newtons. It's one of those tricky ones that people forget. Mass is measured in kilograms and gravity is measured in newtons per kilogram. And on Earth is generally about 10. It's closer to 9.8, but in the exams to make things easier, they might just use 10. Now they might give you this value, or they might decide to be mean and not give you this value. So it is worth remembering that gravity is 10 newtons per kilogram. And because it's one of those tricky ones that the units are tricky ones to remember, there's a little trick that you can actually do. So we can take our equation, weight equals mass times gravity. We can rearrange that to make gravity the source of the equation. So to do that, we need to divide by mass. So we get weight over mass equals gravity. And now if you want to find the units, we just replace the words with the units. So weight, the unit is newtons, and mass, the unit is kilograms. So gravity is newtons divided by kilograms, so the unit for gravity is newtons per kilogram. One that confuses people a lot, here we have work done, we have force, and we have distance. And work done is in joules, force is measured in newtons, and distance is in meters. EK is kinetic energy. Half is just half. M is mass, and V is velocity. So kinetic energy is just energy, it's measured in joules, mass is measured in kilograms, and velocity is measured in meters per second. Now this is a tricky one, people always sometimes get stuck with this because we have the squared and we have the half in there, but just treat it as a maths equation and you'll be fine. Here we have EP, which is potential energy. We have mass, we have gravity, and we have height. Our units for this, gravitational potential energy, is just joules because it's still just gravity. Mass is in kilograms, height is in meters, and gravity or gravitational field strength is newtons per kilogram. There have been a large number of recent advances in car safety. So some of the things that are now in cars to make them safer are seat belts, crumple zones at the front of cars. Because if we're thinking back to our F equals ma, the force that you hit with is affected by two things, your mass and your acceleration. Now we can't do anything about the mass of the car, but we can do something about the acceleration of the car. So if you have a crumple zone at the front that squashes and takes it just that little bit longer for the car to actually hit, you're going to be reducing the acceleration due to the crumple zone, which means the force that the car is actually going to hit with is going to be reduced. Other things are airbags. Again, that is all about reducing the force that someone hit with, so it is going to be increasing the duration of the time that it takes to hit, so the force that you hit with are going to be lessened, and child seats. The stopping distance of a car is affected by two things, the thinking distance and the braking distance. And there are a number of different factors that can affect both the braking distance and the thinking distance. Thinking distance is going to be negatively affected by things like how tired you are, things like alcohol, recreational or medicinal drugs. Now you have to be careful with this one because something like caffeine could positively affect the thinking distance. So when you're talking about this, you always have to be really, really clear whether it's a negative or a positive effect that something is happening. Other things that can affect thinking distance are being distracted, using your mobile phone. So as thinking distance increases, the stopping distance is going to be greater. The other part of this is braking distance. So things that affect braking distance are going to be how fast the vehicle is travelling. So the faster it's travelling, the longer it is going to take to stop. Adverse road conditions, if it is wet, if it is icy, and how your vehicle is maintained. So things like worn brakes or worn tyres are going to take longer to stop the car, it is going to be less effective, and you're going to have a greater stopping distance. There are 3 different types of radiation you need to know about: alpha radiation, beta radiation, and gamma radiation. Now, alpha radiation is 4-2, and this is a helium nuclei. This is like a big billiard ball. It is big, it is heavy, it is reckless. It is very ionizing. But because it's really big, it can't get very far, so it is stopped easily by skin or paper or anything else. Beta particles weigh nothing and have a charge of -1, which you should be familiar with as an electron. These are kind of like mildly ionizing, and they're stopped kind of easily. So they're going to be stopped by something like aluminium foil. And gamma radiation is a wave. So this isn't very ionizing, but it needs something like a thick coating of lead to stop it. Now, gamma radiation can be used for things like cancer treatments because it can get inside a person. And then when it gets in there, it can destroy the cells that it is targeted at. Beta radiation can be used for things like medical imaging. So you can swallow a medical tracer, and because it will get outside your body, the doctors can actually look at where it is and can use that to detect any problems. And alpha radiation is used for things like fire alarms. Now, different things happen when things undergo alpha or beta decay, and you need to be able to do the maths for this. Now, it looks scary, but trust me, it's not. We're just going to take things row at a time. So top row, row. So 228 minus 4 is going to give us 224. 90 minus 2 gives us 88. We can then use our periodic table and look up what is going to have an atomic number of 88, and thorium, when it undergoes alpha decay, is going to turn into radium. Now we have potassium undergoing beta decay, so top row again, 40 minus 0 is still 40. 19 minus -1 gives us 20, and from the periodic table we can see that that is calcium. And this new model of the atom said that there was a positive centre and then everything else around the outside was negative. And this was the first indication that we had of our current day structure of an atom. These days we know that we have protons, which have a positive charge. We have neutrons, which have no overall charge, and we have electrons, which have a negative charge. And the protons and neutrons are in the middle, and the electrons are whizzing around the outside. Nuclear fission is breaking things apart to get the energy out of them. So we fire a neutron at our nucleus, it breaks apart, and out comes some other neutrons, which can then go on and do more reactions and some energy. Now these neutrons here are then going to go and smash into other nuclei, which is why it is called a chain reaction. Now, a lot of energy comes out of this. The source for this is uranium, which we can get from the soil, so it is not a renewable energy source, but it doesn't let off any carbon dioxide, so it is not a polluting way of producing energy. The problems associated with this are going to be things like storing the radioactive waste, because it's still very, very dangerous for thousands and thousands of years afterwards, so we need somewhere to store it and we need to secure it safely. Other problems with this are potential explosions. These can be very harmful, very dangerous for the local population, local wildlife as well, but the advantage is that it just gives a lot of clean energy. Well done for making it to the end, guys. That was a bit of a hard slog. If there's anything I can help you with, please let me know. If you want some extra extension materials, pop over to my website and get my book, or you can go and check out the P2 and P3 versions of this video.